Hi, this is Module 17 of Mechanics of Materials Part 1. Today's learning outcome is to derive the equations for stresses on inclined planes for the case of plane stress in general. And so this is where we left off last time. We had our stress block in plane stress. We wanted to look at the stresses on a inclined surface. And so here was the result. We came up with a sign convention for both normal and shear stresses and the angle. And I said last time, I showed a couple of parts in the last module. In general, we can find from the external loading condition what the shear and normal stresses are on an X and a Y plane. But we want to be able to then transform that into any arbitrary plane to find what the stresses and strains are, the stresses, normal stresses and shear stresses are on any arbitrary plane. And so we want to find sigma sub n and tau sub nt. So here again is my inclined plane stress block. This is known. We want to find this. And so what we're going to do is we're going to go ahead and apply equilibrium. But to apply equilibrium, these are stresses, which are forces per unit area and not forces. And so how would I change these into forces? And what you should have answered is we need to multiply these stresses by the area that they're acting on. And so I've shown the areas here. We'll call the inclined area dA, and therefore the surface, the x surface is dA cosine theta, and the y surface is dA sine theta. And so now I've shown my stress block with forces acting on it instead of stresses. So now let's go ahead and apply equilibrium to our stress block. This is our coordinates, and here is my stress block with the forces shown instead of the stresses. And so let's start by summing forces in the normal direction. I'll call up and to the right positive. Set that equal to 0. For purposes of summing these forces, I'm going to put the angles in here. By geometry, this angle is theta, and this angle is theta, and this angle is theta. And so if I sum forces now in the normal direction, I have sigma sub m dA in the positive normal direction. This force along the parallel to the inclined surface is completely in the tangential direction, so it has no impact on this equation. Let's take this force, which is in the negative normal direction, and it's going to be the cosine component. So we've got minus sigma sub x dA cosine theta, and it's the cosine component. And then so we've taken care of this force. This force has no effect. We've taken care of this force. Now let's do the dy dA sine theta, and it's the sine component in the negative normal direction. So we've got minus sigma sub y dA sine theta times the sine theta component. So that takes care of that. Now I've got the shear stress. It's going to be the sine component in the negative normal direction. So I've got minus tau xy times dA cosine theta. And it was the sine component. And then finally the last force is this shear force. And that's going to be minus tau yx dA sine theta times cosine theta component. And that all equals 0. You can see that every term includes a dA, so let's cancel those out. So there's a dA, there's a dA. And let's leave sigma sub n on the left side, carry all the other terms to the right side since they're negative, and we'll end up with sigma sub n equals sigma sub x cosine squared theta. So this is sigma sub x cosine squared theta plus sigma sub y sine squared theta plus sigma sub y sine squared theta. We know by equilibrium that tau xy and tau ix are equal, so we've got two terms here. So it's going to be plus 2 tau xy sine theta cosine theta. And we're going to use some trig identities here. Cosine squared theta is the same as 1 plus cosine 2 theta over 2. Sine squared theta is the same as 1 minus cosine 2 theta over 2. And you can find these trig identities online or in any trig book. And finally, sine theta cosine theta is the same as sine of 2 theta over 2. And what we get as a result, if we simplify that down, is that sigma n, the normal stress on the inclined surface, is equal to sigma sub x plus sigma sub y over 2, and then plus sigma sub x minus sigma sub y over 2 times cosine 2 theta, and plus tau xy sine 2 theta. And as I said, we know the xy terms all on the right-hand side, so that allows us to find the normal stress on any arbitrary plane. And so that's one result. I would like you to do the same thing for summing forces on your own in the tangential direction, then come on back and see how you did. Okay, so you should have come up with this equation, and you could have reduced it down to this. Sine theta cosine theta, again, is equal to sine 2 theta over 2. Sine squared was 1 plus cosine 2 theta over 2. Sine squared theta was 1 minus cosine 2 theta over 2. And here is our result, which is now the shear stress on the inclined surface. And again, we know all the values on the right-hand side, and so we can find the shear stress on the inclined plane. And so here is our overall result. We now have what's called the transformation equations for plane stress. And we can find for any plane at any angle theta what the normal stress is and what the shear stress is. And so that'll be real important as we analyze structures, analyze engineering parts, to find out where's the max, the min, what angle they occur on. And now you have that tool. And so to finish up for today, I'd like you to go ahead and do this worksheet, which is an application of what today's module was about. And when you finish, I've included the solution in the module materials. See you next time.